Andy Shaughnessy, Content Architect with Printed Circuit Engineering Association. Today, my guest is Karen Burnham, founder and president of EMC United. Welcome, Karen.
Thanks so much for having me.
Karen's an EMC engineer. You've been consulting in the aerospace, defense, automotive industries since around 96. You're also speaking at upcoming PCB East show in Worcester, Massachusetts. Try to say that 3 times fast. On your website, you say you founded EMC United to help make EMC less painful for PCB designers. And there does seem to be some pain around EMC. But what are some of the biggest challenges in EMC right now?
Yeah, so when I'm putting together the class for PCB East, I wanted to focus a little bit on EMC fundamentals. PCB East and West have so much amazing content on signal integrity. And EMC and signal integrity are almost always pulling in the same direction, right? If you do something that's good for EMC, it's usually good for signal integrity, and vice versa. But EMC tends to pop up at a little bit lower frequencies. So the vast majority of problems that I see and have to deal with are between like 150 kilohertz and 1 to 6 gigahertz. But the problem is that like every single consumer electronics device, not even electronics, every single consumer device that uses electricity in the United States has to meet FCC guidelines. And FCC, the place that most people have trouble with is radiated emissions between 30 megahertz and 1 gigahertz. And so that's the area of spectrum that gets the most scrutiny because you're either in North America trying to pass the FCC or you're in Europe trying to pass CISPR 32, which is the equivalent. It's also the spectrum where EMC problems are really easy to pop up. And it's also, like I say, the area that gets the most attention because you have to test there. So trying to work through the fundamentals to show people what are the things that are most likely to cause problems in that specific frequency range, and then kind of how to spot that in advance in your designs and avoid it before you wind up in the situation where you design this beautifully functional piece of hardware, threw it in the EMC chamber for EMC testing, and you found out that it failed, and now you have to make all kinds of really ugly, fixes to it. That's really the goal.
And now a word from our sponsor. Join the electronics design and manufacturing industry at PCB East 2026, coming April 28th to May 1st to the DCU Center in Worcester, Massachusetts. Sponsored by the Printed Circuit Engineering Association, PCB East features more than 120 hours of expert electronics design, manufacturing, and assembly training. The annual one-day exhibition will be held April 29th and features major semiconductor companies such as AMD, Altera, Lattice Semiconductor, Microchip, and Samtec, along with leading software developers and manufacturers. Registration for the conference and exhibition is now open. Be sure to book your spot. For more information about PCB East, visit pcbeast.com.
One of the notes on your website, you say EMC isn't that difficult, but it is counterintuitive. What do you mean by that?
Yeah, so the more I've gotten into EMC, one of my skill sets is translating EMC to English because I'm sure you've heard, Andy, the whole EMC is black magic thing, right? Why do you wiggle one cable and all of a sudden your results change by 10, 12 dB, which is, literally going up and down by a factor of 10. It's ridiculous. And so, if your intuition is set at DC circuits, then that is going to seem like bonkers town. But once you get a feel for how things behave at these slightly higher frequency ranges, and again, considering how much, folks who are exhibiting at PCB East are going to be showing, interconnects that are good for 224 gigabit per second, communications. Right. I don't want to say high frequency, when I'm in the same room with those folks. But again, these moderate frequencies, 30 megahertz to a gigahertz, things just behave so much differently than they do at DC. And so, parasitic interactions, so, the fact that just your body has capacitance. And so as soon as you reach over to touch a cable, you've already affected the system. And that's one of the reasons why it looks like you wiggle just this little thing and your results change dramatically. I've been doing some research for a new batch of seminars that I'm working on, and some that I'm working with Dan Beaker, who I don't think is going to be at PCB East this year, but should be at PCB West. Lots of people know Dan. He's amazing. But as I was doing some digging, did you know that if you derive Kirchhoff's laws, your basic, all the currents into a node have to sum to zero kind of stuff.
Right.
If you derive those from Maxwell's equations, which is not fun, I don't recommend anyone actually do this, but if you were to do it,
Right.
Parasitic inductance shows up directly in the current version of Kirchhoff's laws, and parasitic capacitance shows up explicitly in the voltage version, where voltages and loops have to sum. But the thing is, when we teach EE for the first time, we leave that out. Right? We just teach currents, currents flowing in specific wires into specific nodes, and we skip the part about parasitics because at DC it doesn't matter, and that's for the advanced class. Except for a lot of people, that's all they get, right? They don't get the advanced class.
Right.
And so trying to bring that forward a little bit, because again, it's not, once you know what to look for, it's not crazy difficult. But knowing what to look for is something that most of us only get that experience the hard way, right? By troubleshooting.
Right.
And so it's something that I feel really strongly about, taking everything I've been able to put together, troubleshooting and doing design reviews and stuff between, again, automotive, aerospace defense, medical, all these other things, trying to put that together in a package that can be communicated relatively quickly and simply. Again, there's no substitute for experience, but if you can give somebody like a little bit of a head start.
Right. So why don't you give us just walk through some of the things that you're going to cover in your class at East?
Yeah. So, I want to start a little bit with field theory. When I say it that way, it sounds so dense, right? But what are the electrons actually doing in a circuit? And what we'll quickly realize is that as we move electrons around on our traces, which is what we're all doing with all our PCBs, they necessarily create electric, magnetic, and electromagnetic fields.
Right.
And once you see where those are happening, you'll also start to see kind of naturally how to control them. Because the great thing about moving into these higher frequency ranges is that all these fields that we're generating and that we can't not generate, right? Because we have to move the electrons around. And when electrons move around, they naturally have to generate these fields. The thing is, at higher frequencies, they want to contain themselves in transmission line structures. That's what the higher frequency stuff just naturally wants to do. And when I say higher frequency, I mean like above 10 kilohertz, right? Above human audio range.
Sure.
Yeah, this doesn't have to be crazy high. And so once you start to see and visualize that, and you start to understand how a lot of PCB structures can really easily become transmission line structures if you just kind of design with that in mind.
Right.
That helps contain these fields so that they don't go wandering all over the place to cause trouble, either in terms of crosstalk or getting out on cabling and causing radiated emissions, or stimulating slots in ground planes and starting to radiate that way. And basically, the thrust of a lot of what I'm going to be talking about is, understand a few relatively simple basics, that, how these fields are generated, so you understand where this is all coming from, and then make more transmission lines and less antennas. That's really what I'm going for.
And one of the things that we've seen is that there is this lack of education in EMC. You're one of the few people who are out talking about EMC. Why is there this disconnect, you think? There's all kinds of signal integrity engineers, not a whole lot of EMC engineers.
It's always surprising to me that there's a numeric disconnect, because in my mind, again, the signal integrity and EMC folks are always pulling in the same direction. A lot of times we're going to the same conferences. There's more attention sometimes on signal integrity because if you are into high-speed electronics, you can't skip it, right? Signal integrity is not optional at that
Right.
point. Whereas in EMC, and this is another thing I actually emphasize in a lot of the classes I teach, man, you can do things wrong for a long time until it finally bites you. So, people say, I've been using this design for years. Why am I failing EMC now? Well, probably it's because you put in like a new chip that was a little faster, had slightly better rise and fall times. Or one thing we've seen a lot recently is people, have a basic layout design that's always worked for them. And now they put in a silicon carbide or gallium nitride chip. All of a sudden, that is 3 orders of magnitude faster. And so you're generating all this extra, high frequency noise that your previous design that just always worked, it wasn't designed to handle that. So again, unless you understand those trade-offs, again, so you can have a design that's awful. And unless the Swiss cheese lines up just wrong, right? You can get through EMC testing until you don't. And that's the thing. I run into a lot of companies who are like, well, we don't need EMC people. Our stuff just always works. And I'm like, right, because you're getting lucky.
Right.
But, as you get into more sophisticated designs, and especially as you move to stuff that's, more modern and has faster rise and fall times, faster switching, higher current switching, switch mode power supplies, all this stuff, you're just less likely to keep getting lucky.
Right. We'll go to trade shows and ask 10 designers, should people do EMC analysis? Oh, yeah, we're doing cutting edge stuff. Do you do it? They go, well, if there's a problem,
Well, I
and
will
it's
say
baked
the
in the
other
cake.
thing,
They expect there to be a problem.
right?
And they just wait till there's a problem and then they send it out because they don't have the SMEs anymore because everybody's retiring.
Unfortunately. Well, the other thing is that there's some great computer simulation tools for signal integrity. Stuff that'll just read in your designs and tell you flat out your impedance is off the charts here. You're going to have crosstalk over here. Like, just nailed it down. We don't have that for EMC yet. And it's because of all the parasitic interactions. It's because if somebody walks next to it, the parasitics change. And if you change the housing just a little bit, make it a little bigger, a little smaller, all of a sudden the parasitics change. So there's more variables that have to be captured at very different scales. So to truly fully capture the EMC of a system, you have to be able to do the sub-millimeter scale for the PCBs and also the centimeter scale for the enclosure and the meter scale for the full place where it's installed or test chamber or what have you. And putting all those pieces together in a single computer simulation is still just an enormous challenge. And so, it's easier for people to, kind of do some stuff and wait for it to break and then, fix it when it breaks.
It sounds like it's something AI is not going to be able to make a lot of inroads with EMC for a while, right? Because so much of it is just human judgment, right? You don't know till you know, right?
Well, and the other thing is, until we can simulate it really accurately, where do the data sets to train the AI come from? I expect in my lifetime or in my career lifetime that AI will contribute a lot. And what I would especially love is if somebody was able to use AI to make better, more sophisticated rule checkers. Because some of the software packages, will have EMC rule checkers that go, okay, is there a nearby ground plane? Did you route too close to the edge? Just checking for simple things. But when I've asked people who've used those, they're like, oh man, they throw up like 500 red flags and you don't know which ones actually matter. And it's not that useful to me. If we could get AI to do a more sophisticated version of that, that would be awesome.
And that's why, we really can't blame the EDA companies because they all provide, if you get the enterprise level tools, they all have some sort of EMC analysis or measurement or modeling or whatever.
Yeah, the tools are out there, but, they're still, kind of clunky to use. And again, unless you kind of know what you're looking for, it gets tricky to spot it.
When you have these classes, what sort of problems do your attendees typically come to you with?
The radiated emissions, like it's, depending on who you ask, like 60 to 90% of hardware fails EMC testing the first time. And of that, it's like 75% either radiated emissions or radiated immunity. So that's really where I focus the talks mostly. And then, I get a lot of a lot of questions that are just fairly nitty gritty about why does the standard say to do this? Why am I supposed to do this in one situation, but not in this other situation? And again, one of the problems is that there's a lot of apparently contradictory advice about EMC. For instance, one of the things that I get, I put together a whole day-long seminar just to address this one question, which is, should I connect my cable shield at one end or both ends? The thing is, people will say, oh, well, I've got this reference or article or textbook chapter or whatever that says one end. And here I am saying two ends. I know what that thing says. But if you read a little more carefully, it's either saying in the situation where you are actually directly connected to Earth, like the actual dirt in the ground, or you're dealing with audio frequencies. Especially because so much of my career has been in mobile stuff, right? Military standard defense, aerospace, stuff that's flying, automotive, stuff that's driving. I'm not usually the audio person, and I never have an Earth connection. So I'm like, both sides. Both sides. But even then, I'll tell people both sides, and then it turns out my advice is wrong because that's really only true if you have metal enclosures. Housed in plastic, ground your shield at both sides. You're grounded to probably your PCB ground. It's the only thing to connect it to. And in that case, you really can cause problems. So there's so many subtleties to it that, again, unless you kind of take a little extra time to dig into the fundamentals, it's hard for people. Understandably hard, right? Should they listen to me? Should they listen to Henry Ott? Should they listen to Todd Hubing? And, we all might give you different advice because our default settings are a little different. Right, where each of us is making a slightly different assumption about the system we're talking about. And if we haven't made that extremely explicit, then you're like, oh, okay, well, I'll take that advice and apply it to my system. And it turns out that's not the right advice for that system.
What are a couple of things that you wish that design engineers would do? What, as far as do's and don'ts, what would you say are your top do's and don'ts for EMC for these engineers who maybe don't do this? They're not EMC engineers.
The first advice is the same thing you'll hear from not only every other EMC engineer, but every other signal integrity engineer: solid planes. Oh, dear Lord, we could clear up so many of these problems with solid planes. And I know that the data sheet tells you to split, but the data sheet's probably cut and pasting a reference design from the 1980s that worked fine then and still works fine in terms of their chip functioning, but they do not care about whether or not you pass EMC testing, right? That's not... When they provide a reference design in a data sheet, that is not what they're thinking about. But again, I don't blame people for following the data sheet, right? The data sheet is telling you something specific about the part you are looking at, whereas, me over here being the EMC educator, I'm saying something general. And so rightly so, most of the time you would prefer to follow the more specific advice. So Todd Hubing runs a fantastic website, learnemc.com. Lots of seminars. He's an emeritus professor who's taught this stuff for a long, long time. And when I first started going to EMC conferences specifically back in, this would have been 2012 when I first met Todd, he had examples of data sheets from 2011 that, had horrible advice in them for EMC purposes. And I was at the same kind of conference just this past summer in Raleigh, North Carolina, and I was watching one of Todd's talks because I always learn something. And he had some data sheets from 2024 that had horrible advice in them that would almost guarantee you fail EMC testing. Again, unless people understand more of the fundamentals to see where their design might be badly impacted by these reference designs, it's still going to be a challenge.
Right. What would you say would be your top advice for someone when someone's starting out, they just graduated, they're a double E, they're coming in and they're actually kind of interested in EMC. What would be some advice you would give them?
By the way, let me just say that the generation of engineers coming in at this point are amazing. They have such a drive to do things well, right? They are investing in their own education in a way that their companies may not be supporting. One of the things I see in the training seminars that I give is a lot of people are there on their own dime and their own time. And I'm like, I do not feel like these folks are getting the credit they deserve for being proactive about trying to get out there and really understanding how to be the best design engineers they can be. I just want to give a shout out because every once in a while I'll hear somebody of an older generation kids these days, they don't know what they're doing. They're just
Right.
lazy. They blah, blah, blah. And I'm like, well, have you invested in training them? And
Mhm.
they're like, oh, no, we don't have budget for that.
I talk to kids that are freshmen getting in the EE program, and they've already built circuit boards as part of building drones at the Maker Faire.
Oh, yeah.
The circuit board is just a means to an end. They know how to code, they know something about embedded, they know a little of this, a little of that, because it's all online. I mean, we grew up, there was no internet,
Right.
These kids we want to learn it, like there's somebody teaching it.
Going out and finding, finding one of the basic classes. And you mentioned there's only a handful of us, but we're not hard to find. We really try and be very easy to find for obvious reasons. But myself, Ken Wyatt, Todd Hubing, Dan Beaker, Rick. Oh, if you ever get a chance to see one of Rick Hartway's presentations, I mean, he is so good and he knows so much. And finding like a 1 day or one of the ones that's like a couple hours a week over multiple weeks or multiple days, something that's got a relatively low barrier to entry, but it'll just give you that sense of the basics that you didn't get in college. It's that little, of that, we don't have to cover that in DC circuits. We'll leave it for the advanced class. And then you never got to the advanced class where they cover it. Investing in one of the little seminars or something, or when you go to a conference, finding one of those educational tracks where you can just get that.
Anything else you'd like to add as far as the class or anything else?
Well, I mean, I always look forward to the PCB East and West conferences. They are always a good time. And like I say, I go to listen to the other speakers whenever I get a chance because I always end up learning something. Really can't say enough good things about the value I've gotten from PCB East, East and West. I'm really happy to be able to contribute some to that now. And yeah, I hope if anybody's there that they come up, introduce themselves, sit through part of one of my lectures or one of Rick's or one of Susie Webb's or, all these amazing people. And I'm really looking forward to it.
Well, maybe you'll inspire some of these young people to become EMC engineers. Right?
And I sure hope so, because like I say, the challenges are not getting any easier, and there are not enough of us.
All right. Well, thank you so much for speaking with us today, Karen. This has been really fantastic. Look forward to seeing you at PCB East.
That sounds great. Thanks so much for the invitation. It was great talking to you.
Oh, great. This is Andy Shaughnessy for Printed Circuit Engineering Association. Have a great day.